In the world of high-performance computing and gaming, we obsess over every millisecond. We optimize shaders, prune draw calls, and refine algorithms. But there is a silent thief lurking in the background: telemetry. Telemetry is the eyes and ears of modern software. It tells developers how their apps are used and when they crash. However, the act of observing a system inevitably changes its behavior. In this video, we are exploring the CPU overhead of surveillance. We'll look at how simple logging, metrics gathering, and phone home features can devour your frame budget. When a CPU is busy packaging data for a server, it isn't rendering your game. This is the trade-off between visibility and performance, and often the price of knowing everything is losing the very fluid experience you're trying to measure.
The first major overhead source is data transformation. Software doesn't just send a raw memory address to a monitoring server. It has to serialize it. This usually means converting structured data into JSON or protobot formats. This process is surprisingly expensive. It involves string allocations, memory copies, and heavy traversal of object trees. While the main thread is trying to finish the current frame, it might be blocked waiting for a telemetry buffer to flush. If your game generates 10,000 events per second, and each event takes 10 microseconds to serialize, you've just burned 100 milliseconds of CPU time, far more than the 16.6 milliseconds allowed for a 60 FPS frame. Even when offloaded to a background thread, the sheer volume of memory bandwidth consumed by these buffers can starve the GPU, leading to stuttering and inconsistent frame times.
Modern CPUs are masters of multitasking, but multitasking isn't free. This is the context switch problem. When your application pauses its primary logic to send a telemetry heartbeat, the CPU must save the current state, load the telemetry task, execute it, and then swap back. This swap flushes the CPU's L1 and L2 caches, which are filled with your game's critical data. When the game resumes, it suffers from cache misses, forcing it to wait for slow system RAM. Furthermore, high-frequency telemetry often relies on system interrupts. Every time a network packet is sent or a timer fires, the kernel may preempt your high-priority game thread. In a dense environment, these micro-interruptions add up to a death by 1,000 cuts, where the CPU is so busy managing the monitoring system that it can't maintain a steady clock speed for the actual work.
To see the real impact, we look at the benchmarks. In a clean environment, the CPU frame time is consistent, but as we add layers of surveillance, cross-reporting, analytics, and anti-cheat, the frame time variance skyrockets. Notice the difference in the 1% lows. While the average FPS might only drop by 10%, the stutters become twice as frequent. This is because telemetry often fires in bursts. When a player levels up or opens a menu, the system sends a wave of data. This bursty nature is what kills the feeling of smoothness. In this table, we compare a standard build against a heavily instrumented one. The increase in system calls and memory pressure is undeniable. For a competitive gamer, that 5 millisecond jitter caused by a telemetry flush is the difference between a hit and a miss. There's a philosophical irony here, known as the observer effect. In physics, the act of measuring a particle changes its state. In software, the act of measuring performance consumes the resources needed for that performance. If you use a profiler that is too heavy, it will show your code is slow, but it's only slow because the profiler is running. This creates a feedback loop. Developers see slow performance, add more telemetry to find the cause, and the performance gets even worse. To break this cycle, we must move towards passive monitoring. This means using hardware counters and low-impact sampling instead of active instrumentation. If your monitoring tools are visible in your top-level CPU usage, they are no longer just observing the problem. They have become the problem.
So, how do we monitor without murdering FPS? The answer lies in two techniques: sampling and batching. Instead of logging every single event, we sample. We might only record data from 1% of users or every 100th frame. This statistically represents the whole without the 100% overhead. Second, we batch. We store events in a lock-free ring buffer and only process them when the CPU is idle, or we send them in one large compressed block every few minutes.
By moving telemetry off the critical path and into the gaps between frames, we can maintain visibility without sacrificing the player's experience. Efficient telemetry should be invisible, acting like a silent passenger rather than a demanding navigator. Telemetry is a tool, not a requirement. When used poorly, it creates a surveillance state that punishes the user with lower performance. As developers, we must treat CPU cycles as a finite, precious currency. Every line of monitoring code we add is a tax on the user's hardware. By understanding the costs of serialization, context switching, and the observer effect, we can build leaner, faster applications that still provide the insights we need. The goal isn't to stop measuring, it's to measure with intention. Thank you for watching. Keep your frames high and your overhead low.